So, this work has been going on with the first line is my former students, and Shashwati is finishing now, she is here, and these are the other collaborators, Satoshi Nawata, and then the Russian group Mironov, Morozov, Sleptov, and so, who is Chinese, who was involved in the entanglement project. So, I thought I will put in all the essential connections, how Chern-Simons theory seems to be, in a calculable framework in various contexts and what it connects to. Okay, and essentially, like the particle data book, there is a knot data which keeps getting updated because various conjectures like Oguri-Waffa conjecture to verify and so on, we have verified and we have tabulated it for various knots up to 10 crossings, and it could be used by others without worrying about it in the context of finding the BPS counting, M2 brane, M5 brane intersections and all. You can use that data. So, you do not need to start ab initio doing the, it is like CG table, you can take it like that. So, it is updated and we wanted to go up to 12 crossings, but it becomes exponentially growing. The knots, it's in 3 crossing, it's only one non-trivial knot, but if you go to 4, there is 1, but from 5 there are 3 and so on. It keeps increasing, and at 10, how many are there? Like 220, huh? 165. So, it keeps going very exponentially.
So, are there parameters which label these degenerate knots at a given number of crossings?
There is no parameter, just like a periodic table, calcium, strontium, the way you given table, they given a table with 10 subscripts.
Atomic weight can distinguish the isotope.
Yeah, there is nothing like that, but they have tabulated called the Rolfson table. So, the 10-1 means this is the knot which will be universally followed.
I don't quite understand the word tabulation when one cannot classify.
Yeah, this is the way they had, the original guy had tabulated and he had given a name to it, and we are just following that name. Nobody is changing it, that is all.
So
there is no.
Increase the number of crossings, you need more and more information to characterize the knot, right?
I am not sure whether we need more and more information, but how many topologically distinct such curves can be drawn with only 10 crossing, if you ask us a puzzle question. And one person has tabulated it and he calls it as 10-1, 10-2, 10-3, and there is no such distinction as parameter. No, it is serial number, and that serial number is strictly followed. If I say 10-22, I will not use one different knot from the other guy. I will go to the table and.
The growth in degeneracy of knots with crossing?
There are open problems with knot theorists are trying to look into it,
so
but
it's not
yeah, it's not certain. Only what I am saying is that the table is available and I can work with that table. Okay. So, that is why I am saying that this knotebook.org website, we keep periodically updating whatever knot. It is not that we could find out the polynomial form for arbitrary representation put on the knots, and we do it from time to time, whatever we do, we update it.
Crossing means crossing in a two-dimensional projection?
Correct, correct. Yeah. Yeah. So, essentially it is a, if you treat it like a 2+1 dimensional theory, in 2 space and 1 time, you do exchange. If you want to exchange 2 particles, you can do a clockwise or an anti-clockwise. You can call clockwise as an overcrossing and anti-clockwise as an undercrossing, and you draw that as a projection in a 2-dimensional plane. Okay. Yeah, so this is very special to a 3-dimensional theories. All these knots are non-trivial only in 3 dimension. Okay. So I hope there are students here also. If you have, it's just the general knot which you see in day-to-day life, but only thing is that the endpoints are not free. That is also tight. They are identified. Okay. Okay, so I will give a brief overview of what is Chern-Simons role in getting the knot invariance, and then is completely a different task. In fact, there are a lot of interesting open problems which I have not been able to tackle here. If anybody is interested, I can talk there. the SL2C Chern-Simons, these are SU2 Chern-Simons, SU3, SUN, SON and so on. The complexified groups have a lot more information on not only this volume of that 3 manifold, but you can also get more information about the SL2C character variety and also get the full partition function. Okay. So, there are some things which Gukov has mentioned in 2003 paper. It's still unclear how to go about in finding the H cross expansion, 1 over H cross expansion for the total partition function. Okay. So, in that sense the volume conjecture is very interesting. So, I will try and show how the knots are connected to the volumes of 3 manifolds. And then finally, with a lot of current development in quantum information theory with entanglement between qubits and 2 qubits, 3 qubits, there seems to be a lot of rhythm in the context of tracing out one of the components in these links and so on. So, I will show you pictorially and also how we quantitatively compute. Okay. So, this is a plan. So, I am going to take the 3 manifold to be a simple 3 sphere S3, okay. And this is the Chern-Simons action. It is a 3 form on any 3 manifold, but I will take this 3 manifold to be S3. And A is the gauge field, and you can choose the gauge field as matrix valued in any gauge group. You can take it to be SU2 or SU3 or any other groups, any compact. We would like to take it to be a compact group. Okay. So, this is the action for the Chern-Simons theory, and you can see from this action it is explicitly metric independent. So, there is no notion of distance. Any observable small size, big size in this theory will give you the same answer. So, that is why it is called as a topological quantum field theory, because it is explicitly metric independent. Okay. So, for example, I have drawn a figure 8, this is what they call it as figure 8 in the knot table literature, or they denote it by 4 subscript 1. So, you can take this knot and I put it inside the S3, and you can take this knot with carrying a representation R, any representation of the group, gauge group, and let us confine ourselves to SUN for clarity, and we want to look at a metric independent and a gauge invariant. It is a gauge theory. So, I need an observable which is metric independent and gauge invariant observable, and that is nothing but the Wilson loop operator. So, what you have to remember is that these MUs are valued in this representation R, and then you take the trace over that representation R. Is that clear? So, this is another knot which has 3 crossing, which is a trefoil. I have just put it for just to show you some few examples.
Just a quick question. What is the knot here? Because this is some Wilson loop that you wrote, right?
Yeah.
So, in the equation.
So, this is the integral over that curve, and that curve is the knot.
Okay, so this is not a 2-dimensional. It's not a tube. It's a line, right? That's what.
It's a line.
Okay.
Yeah, it's a line. I have just drawn it as a tube so that you get a feel of it.
Basically a line.
It's a single line. Okay. So, it's just a single line. Yeah.
So it's 4, 1. Actually, there are 4 crossings.
No. 4 subscript 1 is the Rolfson table.
Yeah, so
Okay. So, let
4 is the number of crossings.
4 is the number of crossings. 4-1 is the notation for figure 8.
What does 1 stand for here? I mean, does it have any?
Yeah, that is what I was saying. So, when you go to 5, there are topologically distinct knots.
I see. Okay.
Okay, and then that table is available, and we just follow that whatever knot they are going to call it as. In the case of 4, there is only 1, but still we call it 4-1, and then the below 1 diagram which I have drawn here, this is the 3 crossing, and that is what is called as trefoil. Okay.
So, no matter and how we deform the number of crossings is always a topological invariant when we
Very good.
project it on
Yes.
plane.
Yes. Yeah, you can add some additional twist, like if you take this, let's take a simple loop. I could add a twist like this.
Yeah, that's what I was saying. But this is a trivial thing, right? I mean,
Yeah.
so how do we know that
Yeah,
whether
so this-
crossing is there or not?
Yeah, so this can be undone
Okay.
because you are in 3 dimension. You can always, you know,
Just
undo it, but you cannot undo those things here. You cannot cut and paste. As long as you can pull and do thing, this will be same as
just a circle.
circle. Okay. So if I write an invariant for this and an invariant for this, I want these two should be same. Okay. These are what we call, you can call it as a set of moves which you are allowed to do on any region of the lot. One move is this and nothing should happen. Okay. So the expectation value of such observable, so is this clear? The knot is, so the knot here is that integral over the curve, the loop which I have drawn here. Is that okay? For the different knots you will have the information here. Yeah.
This thing doesn't look like a figure of 8 to me, but maybe in some way of thinking about it is the middle part.
This one because of the driving class. Huh?
But there's a lot of other stuff.
What other stuff?
No, he explained. So the middle part looks like a figure of 8,
Ah.
but then there's some other stuff.
That's right. So that is what is we can, yeah, like the driving test you are talking about maybe. I don't know. Okay. No, the way you said, I thought it was that one which probably rings your mind. Okay. Okay. So let me give it as a table. SU2 gauge group, fundamental representation, whatever is that expectation value we find, this is the work of Witten, it's nothing but the mathematician's work, which is the Jones polynomial. Okay. If you put different representation other than the spin half, if you put higher spin representations, you end up getting new polynomials for the same knots. Like trefoil figure 8 which I have drawn written here, I can write Jones for trefoil, Jones for figure 8, and then it continues spin 1. Okay, so this is one list and you can start listing the polynomials for the, so this is spin 1, this is spin half and so on. The reason why this is being done is, in this table there are many knots where this polynomial turns out to be the same. Okay, if you write a arbitrary polynomial of some degree and if you try to put some value to that polynomial variable, you end up getting same, right? Sometimes it happens. So we do find that these are all different knots, but there are some polynomials which are same, which bothered them, and then Chern-Simons theory seemed to help us out that you can at least live the degeneracy. Any two knots you give, some representation could be different. But even that we disproved for a class of knots called mutant knots, but let me not get into it. But at least it improves the classification. By classification I mean one-to-one onto map is getting improved within Chern-Simons theory, because you can change the gauge group, you can change the representation, and then maybe if in a gauge group and some representation, two knots which are distinct have the same polynomial, in different representation, different gauge group, they will be different. So that way it is improving the classification. Is that clear?
Relatively small knots which are not distinguished by any of these things.
Yeah, that's what I am saying. Everything, there is a class of knots called mutant knots. So mutation is what? You take a region, you give a good twist to it, 180 degree, and put it back. That's it. You take a knot, you remove a region, You give a twist, 180-degree twist to it and fit it back.
So how is it from physics that cannot distinguish it?
Yeah, so this was my long back, my PhD work where we showed this operation is an identity operation. We showed that at least for representations which are symmetric representations or all SU2 representation, it turns out to be an identity operation. But in general we can show for higher, that is what one of the work which I gave a talk 2 years ago I think, where for representation which are mixed representations of SUN, this one SUN, this is like the octet of SU3. If you take this, then we could distinguish. If you take a black box like A connected to B, this is the knot K, and you can have the mirror reflection of it like this, 180-degree rotation, and don't touch the B, only one region, and connect it. This is the mutant of knot K. Okay. What we can show is that this polynomial with this representation, okay, this is not equal to for SUN. This was the work with Satoshi and Vivek. So this was one of the recent work which happened I think 2-3 years ago. Okay. So this is the challenge, and there are a lot of improvements happening because we are doing by Chern-Simons approach.
So is the order of the polynomial determined solely by the number of crossings in a knot, or?
I think the leading order most probably depends on the number of crossings, because it depends on the eigenvalue power. I think that leading order will be on the number of.
See that this kind moves actually lower the power of Q.
Huh, that's right. That's what I am saying.
But from physics, is it clear that there should exist knots which are not distinguished by any of these things, even by colored outline?
This one we thought initially it is not going to be distinguished, but later on we found that there is some, see, mixed representation has one more property. If you take a tensor product of two mixed representations, the irreps which you get can repeat, right?
Yeah.
That is what is called as a multiplicity issue. Okay. That will not happen if you are taking symmetric representation. Symmetric tensor product, every irrep will occur only once, but if you take mixed representations, some irreps can occur more than once. So that multiplicity issue has to be input into the conformal block. So the thing is, usually blindly what we do is, if you take two primary fields in the Vesuvino conformal field theory in representation 1, 2, we say that it gives you an R which is an element of R1 cross R2, right? But you have to also put an additional information, which is what is the multiplicity. So the multiplicity is only 1 for the symmetric, but for this case you will have multiplicity for some representation more than 1. And this information seems to split this out. Okay? Yeah. Okay, the same story on the SUN. There were actually Homefly, and then there was PT also. So nowadays it's called Homefly PT polynomial, and that's for the fundamental of SUN, and then for other representation we called it colored Homefly PT. Okay. And only thing is, you will worry what is this polynomial variable. This mathematicians did not have any, anything associated with what is Q, what is A, and so on. But from the physics approach, the Witten's approach, you can show that Q is related to the Chern-Simons coupling and also the rank of the gauge group, and A is not actually independent, but A can be written as Q to the power of n. Okay. So if I work with a specific n like SU3, then it will be like a one variable polynomial. Only when I write for an arbitrary SUN, wherever Q to the n emerge, I will put a second variable. Okay, so the Jones polynomial, for example, is a polynomial in variable q, and what you see is that each of these coefficients are integers. Okay. So this was one of the things which it appears to be like an accident for some knot, but what is happening is that whether we do colored home fly, colored Jones or any of these things, we find that this thing, this is a Lorentz series expansion with integer coefficients seems to continue. It is not that it is only happening for some particular example, some specific group, for some specific representation. For any representation, any group, it seems to continue. This has been puzzling most of us for the last 15-20 years. There is no underlying reason why the coefficients cannot be fractions, rational numbers. Why is it that it is always becoming integer coefficients? Okay?
This particular kind of knots?
That is what I am saying, it is independent. No, this particular integer is having information about this knot, but whatever happens, it is always an integer coefficients in that Lorentz series.
And this statement is for all class of knots.
All knots whenever you do all representation and so on. Okay. So, what I am saying is, if you write the polynomial for and this is specific to the knot k, and that can be the knot k information, but they are all integers. Okay. It looks like an accident, but why? It can't be an accident for arbitrary knot, arbitrary representation, arbitrary gauge. There should be something underlying. Okay.
It could be negative from this example.
No, it can be negative. I am not saying it is positive integers, but it is always integers. Integers can be positive or negative. Okay. Powers of q? Integers. It can be plus or minus also. Yeah.
Is it even for other age groups like SON or SPN?
Hmm?
Is it only for SUN that also?
Okay. I have not checked for arbitrary cases, but for some similar representations, you know that they are matchable. The symplectic and SON. There you can check. SON, of course, we have checked for some simple representation. This is true in most of the case. Okay.
So in that case, they are not polynomials anymore, right? When they can be, it's when it's generally a Laura series, we can't call it a polynomial. If there's some 1 over q, you said it could have negative.
Okay. So they write it as something like an integer in q comma q inverse.
I see. Okay.
Sometimes they write q to the half and q to the minus half. So it is
So
just
it
a
will be-
matter of definition. Yeah.
But in some definition, it's always
Yeah.
possible.
Other way is that you can pull out that overall constant out and write it as a Lorentz series in integer powers.
That will be a that will terminate.
It will
and-
terminate.
Yeah. That's
It's not an infinite series. Yeah. So then there was you know,
Sorry, and the Jones polynomial, is that the partition function divided by the partition function of the sphere? Or
which one? This Jones polynomial is yeah. So let me write it here. So you write the Wilson loop operator for the knot k, which is partition function, right? And this will turn out to be Jones polynomial for the knot k by, sorry, so this was what we call it as divided by Wilson loop for the simple unknot, which I have to do it as a normalization. Okay, and this is what is the Jones polynomial, just an unknot normalization. Yeah. Because the reason also is that mathematicians call the simple loop normalization to be 1 and then they continue. Whereas when they write two simple loops, they wrote this result as q plus q inverse. Okay. So this is something, if you want to write an expectation value of two simple roots, calling it as q plus q inverse didn't sound fine, because for them one of the loop they called it as 1, okay, and 2 loops I would like it to be 1 into 1, but that is not what is happening. So, we normalize this as n, which we call it as q plus q inverse, and then this becomes n squared by the normalization. So, whenever you have to match with the mathematicians, you have to normalize that by the not normalization, and then it will match with it. Okay?
So these things are interesting only when the 3 manifold is S3, or you can have other guys like S2 plus S1 or maybe solid torus and stuff.
It is not easy to compute, but there is a way of doing it by surgery procedures, where you take a knot in S3 and then how to go to S2 cross S1, you have another imaginary curve where you do a surgery, and there is a procedure. But then it is not as clean as the way we work out in S3. Other thing is that S3 has a trivial flat connection, whereas if you do S3 mod Z2, S3 mod ZP and all, then you need to worry about the space of, there will be many saddle points and so on. So, there are some issues about it. S2 cross S1, the canonical quantization says the partition function is 1, right. You can go to a gauge and you can show that the canonical quantization on Z of S2 cross S1 in Chern-Simons is 1. So, then it becomes more difficult with working with that S2 cross S1. Yeah. So, both the mathematician side and the physicist side have been trying to get some insight on why this is happening. So, the mathematician Konos had this categorification program. Categorification is nothing but like you can add one more extra dimension, which is giving you, one more variable. Instead of q, you will have q and t, 2 variables. And then he tried to write the series. So, all these Jones polynomial which is written, let me call it as Kono, q and t, and this will turn out to be like summation over I and j, t to the power of I, q to the power of j, and then some bigraded homological chain whose dimension of that Hilbert space. Okay. So, and you will ask where you will get the Jones. Jones turns out to be, if you put t equal to -1, then it turns out to be the Jones. This is for every knot. Okay. So, this is the, so this was his argument that you can rewrite it involving a bigraded homological chain, the dimension of it, which will always be a positive integer, and the negative signs are obtained because once you replace t by -1, some coefficients can become negative. So, this is his justification, and he proved this, and it worked even for colored Jones also. Yeah.
So you have 3-dimensional manifold, you have this knot. How are you computing it in 4 dimensions? Like what is t?
Yeah. So, here it is like a additional categorification variable which is being introduced.
What does this mean? Is it that you are extending this horizontal lines in some way?
You can treat it in 4D as if you are doing like a surface operator kind of thing, okay, but here he is not doing that, mathematician is not doing that. So, this is what they call it as a, they break it up into a homological chain, and then everything has a t variable to it, and then they write the tower of Hilbert space for it. Anyway, so at some point I will, if required, I can discuss this with you. Okay. So, I am just giving you the reasons why it can be now justified why they are integers.
This stuff also has an interpretation in terms of Wilson rule, this KHT, T.
No. There is some class of knots where we can do refined Chern-Simons, where we replace the dimensions by, dimensions are proportional to Schur polynomial, and then we can also write McDonald polynomial, but it does not work for arbitrary knot. We have tried this. Refined Chern-Simons have explanation for some class of knots which are the torus knots. Not even all torus knots, some set of torus knots, but not for others. Okay. So that that route of refined Chern-Simons is not helping us. Like what I am saying is that typically on a torus you have an S and a T matrix, okay, and the S and T matrix, this involves e to the 2 pi I by k plus 2 times, I think, quadratic Casimir of a representation, right. What they did is that they tried to replace the CR, e to the 2 pi I by k plus 2 CR, this piece is Q. So Q to the CR, they tried to replace it as Q to the something and T to the something, and when T is equal to Q, they get back this answer. So this is what was done in the refined Chern-Simons. And using that procedure, they can reproduce the Kohanov result for trefoil, which is a torus knot, and other class of torus knots, but not for figure 8. In fact, figure 8 I cannot get by this procedure. Okay. So this is also another reason why they say that all these polynomials I can get from a recursion relation, whereas Kohanov polynomial you cannot obtain by recursion relation. So in that sense they say it is not a combinatorial answer, it is more to do with looking at the homological chain. So it is a very tedious exercise, you know, even for the trefoil if I have to tabulate the homological chain and write it out, I will take another half an hour to explain, but I have some slides I probably talked 2 years ago here, but I can show it. Okay. Okay, so to finish this point, Oguri-Vafa conjecture. So all these Chern-Simons which I am talking in the spirit of ADS-CFT. ADS-CFT, you know that you have n equal to 4 super Yang-Mills on the coincident D3 branes, right. Similarly, you can see that you have a topological string theory and you have S3 topological branes, and on these S3 topological branes you do have Chern-Simons theory. Okay. So Chern-Simons theory, using that route, these integers can be accounted as if it is a counting of number of BPS states. Okay. So in some sense the negative and positive charges you can account by these signs, and in some sense now we have some insight why they are integers. I think 10 years ago Witten had come up with trying to determine these coefficients as if it is the number of solutions to the these equations which are the BHN equations. So he tried to account for it for a specific instant on number n, how many such solutions are there, and there is a way of accounting for it. What I am not able to get an insight there is that I am not able to work it out and show it is 1, 1 and minus 1 even for the trefoil. Even though he makes a statement, it is not clear how to work it out and show that I do get, whereas I have a feel for it where I can work it out at least for 1 or 2 examples. I know it is doable for any example. That kind of a feel, these two I have a feel, but I do not have a feel for Witten's prescription of counting it as a number of solutions. Okay. Okay, so I just gave you like a black box that the expectation values or the Jones polynomial or colored Jones and so on, but the actual calculations is also doable using Witten's 89 idea. One of the barrier in explicitly writing it in variable q and a in the SUN is the quantum 6J symbol. So I will just try to give a flavor of how the computation goes so that you get some idea on this. So typically you take this knot, okay, Okay, so this one if you see it has 1, 2 and 3 crossings. So if you take this knot in S3, you slice it along two S2 oppositely oriented S2 boundaries. So each of the S2 boundaries in this particular case has 4 punctures, and the oppositely oriented S2 boundary also has 4 punctures, and we write the Chern-Simons functional integral on such a 3 ball with such an S2 boundary can be given by some state, and this state is going to be in this vector space, Hilbert space on S2, and the dimension depends on how many punctures you have. Okay. So, especially since there are 4 punctures, you will have a 4-point conformal block as the basis.
Sorry.
Yeah.
So we said conform blocks are the states.
Are the states, are the basis states.
So is it a, can I think of it as a wave functional sorts? Because the state should be given by a wave function. So in what sense is the wave function?
No, this is the state for the Chern-Simons functional integral, and then you have to take the inner product to get a number which will give you the partition function with this observable
Right,
element.
but if I don't want to take the inner product, we just want to consider explicitly describe
Yeah,
the state.
you can do that
What
also.
How would the wave function look like?
It will be, let's say, in this Hilbert space there are these points
Yeah.
which is intersecting. Give them coordinates z, z1, z2 and so on. So if you consider a correlation function with that number of insertions, there will be different channels. There will be different some number of conformal blocks. So the number of conformal blocks will be the same number of independent wave functions that you get. And if you choose a chosen basis of these channels, then there is a one-to-one mapping between a basis of wave functions.
Yeah, so diagrammatically I can show what he is saying. So what I am saying is you can put for the 4 punctures, you can have so this will be the state which depends on, in fact this will depend on the primary fields on the punctures. Suppose I put R1, R2, R3, R4 in general, but in the case of not all of them will become, some of them will become R, some of them will become complex conjugate of R because arrows will change sign. Conservation of charge at every boundary should take care of that. So this R1, R2 will be R, and the other 2 will be R bar, R bar. Which one will depend on the diagram.
Correct. Just
Yeah.
re-ask Abhijit's question.
Yeah.
You know, I think Abhijit was asking that there is an abstract space of conformal blocks.
Yeah.
And we know that the Hilbert space is that vector space of conformal blocks.
Correct.
This, I think everyone agrees with.
Correct.
But Abhijit was asking, and Indranil was sort of addressing, that that the abstract space also has representations as functions of Z. And I think he was asking whether you could think of those functions of Z as being wave functions of something,
Yeah.
which is not just some abstract vectors. But I have a rough comment on that. If you in some situations, depending on particular boundary conditions, if you look at quantum mechanics of anyons on the sphere, that system has an actual Hilbert space where you have functions, arbitrary functions, and in some situations these can be the ground state of that quantum mechanics.
Oh, this can be the ground
The
state.
ground state of that quantum.
I see.
If the norms of such states, then why are they independent of Z?
No, and also it's a topological.
But the state depends on Z. So why wouldn't its norm depend on Z?
It depends on the topology of the norm. When you take the
That's what happens when you think in terms of this Euclidean picture, let's say. But if Z is needed to characterize a state, okay, this is perhaps, I mean, okay, if I think of it from a different point of view, then clearly it doesn't. But why a priori?
The norm includes integrations over Z.
Yeah.
Think of it as particles, 4 particles. You just integrate over that.
Right.
Okay. Okay, so I've just tried to explain it here. So if you have two of them closing like this, then it is a singlet. So the singlet I've shown here. And what normalization I choose is such that the unknot result of the Jones which we have normalized should be got out of this. So that normalization forces us to choose these 80 coefficient to be square root of dimension Q of representation T. Okay. This is a quantum deformation of any dimension. Suppose you had this, the dimension in SU2 you would have said it is 2, but if I do a dimension quantum deformation of this, I will write it as a Q number 2, and this Q number 2 is nothing but Q to the power of 2 by 2. In fact, any n if you have, it is just a deformation.
This is in a very nice, so in a very canonical choice of basis.
In this choice of basis.
What is this choice of basis? Can you say it?
So which choice? I can either choose this choice or this choice in the 4-point conformal block without the S and T channel.
Right, you can choose these channels, but
Yeah.
in this channel there could be multiple conformal blocks in every channel.
How will you have multiple conformal block? You can always break it up into either an S channel or a T channel or a combination of S and T.
And
What else can you have?
from the perspective of the conformal, let's say
Only for 4-point conformal block. I am not going beyond 4-point conformal.
let's look at 4-point conformal blocks.
Yeah.
If you have fundamental and anti-fundamental, if you
Huh.
use them, you can get singlet or adjoint. These are the two channels.
Correct.
Both of them will have their own conformal block.
Sure.
But so then this is a two-dimensional Hilbert space. You need to choose a basis.
Correct.
So in a particular choice of basis, these coefficients will make sense.
No, but it is also dependent on the representation which I put, right? So this T is an element of R1 cross R2.
Definitely, it will depend on all the external representations.
Yeah.
That does not define a basis. So this is like you are choosing a basis in a Hilbert space. Hilbert space is two-dimensional. You are choosing
No,
a
but
basis.
it depends on the punctures, what representation it carries. So the basis also depends on what representation you have put on it.
But
For
does
a
not define
particular,
it uniquely.
no, it doesn't define uniquely, but given a situation, I can choose.
Yes, so
They are all equivalent bases.
they're all equivalent bases,
Yeah.
and you are choosing one of those equivalent bases.
One depending on the situation.
And what is this choice? Looks
This-
like very nice numbers are appearing. This is why I'm
No. This numbers is the normalization such that if I take this with this, I needed to get a unknot result. If this is for this and this is for this. Oh. So
I
this is
understand
all.
that the normalization is determining the numbers.
Yeah.
Looks like numbers are very nice. It's some nice quantum dimensions.
Yeah.
So it is happening because you have chosen some nice basis. Is there a
No,
way of
whichever
organizing what
basis you
have
choose, the dimension of a representation, whether it's conjugate or the same representation, is not going to change.
Yes, the dimensions are not going to change, but these coefficients will change.
Coefficients will change, yes, coefficients will change. To go to the coefficients, I have to also say how to go from one basis to another.
Right.
That
you have
is-
chosen some very, very particular basis.
Ah.
Is there a way of saying what basis it is, like formally, or is it some choice? It is
Any
a
choice you can take, even this basis you could have taken, but this will be related to this by some unitary matrix which relates it. And that unitary matrix also I know what it is, I will tell you that. Okay. Whatever is the choice, you know how to go from one to the other. And you work with a convenient basis where you can do the calculation. Yeah.
And these operators sort of become, if Q tends to 1, then they just become dimension. These are quantum dimensions. So when does it become the actual dimensions?
When the large scale limit,
large limit, which is like Q. going
Q
to 1.
tends to 1. Yeah. So Q tends to 1, it will become
Right.
1. If you take it to be 1, then you will get the ordinary.
Actual limit.
Clear? Anything else? Okay, so then the numbers can be computed in this basis, and as he was already asking me, there are ways of equating these two bases, and these two bases are related by the unitary matrix, and that unitary matrix is not, it has all the properties. This is what we call it as a duality matrix or the fusion matrix. It has exactly the properties of the quantum deformed SU2 if you are looking at SU2 group, or quantum deformed SUN Wigner 6J symbols. Okay. So, Wigner 6J, so what is the Wigner 6J? What is Wigner 6J? Basically is what? If you take 3 angular momentum, you can use the associativity property of combining first the first two and then the third, or combine the second and the third with the first. These are the two equivalent bases for a finite, a specific R, and T and S are the representations. I have shown this pictorially here for the SU2. The algebra familiar to us, the SU2 algebra is familiar to us. Only modification and Q deformation of that algebra is that you won't just get JZ operator, but you, similar to this Q number which I wrote, you Q it. So, in the limit when Q tends to 1, you will get the ordinary JZ, and all the ladder operations are exactly similar to what you do in your SU2. The only modification you have to do is that you have to replace each one by a Q number, okay, not ordinary number but a Q number. It is really beautiful. All the tensor product, if you do spin half cross spin half, if you do it, you will get right. So, you can write Q number 2 times Q number 2 ordinary multiplication is Q number 3 plus Q number 1 is 1. So, all these Q deformation also satisfies the ordinary number tensor product multiplication which you did.
Right, Raman, your previous transparency.
Yeah.
This is probably the discussion you had with Indranil that
Yeah.
I partly missed. These two conformal blocks,
Yeah.
You need to normalize them and set their phase for these
Yes,
things to have meaning.
yes.
Normalization, I presume you have some scheme.
Yeah.
What about the phase? Is there a natural way to set the phase of the blocks?
Okay, phase I think it does not really play a role when we calculate the invariant. Any overall phase factor we do not really worry.
But if there is some relative phase factor between the things on the right hand side, then your A's will change.
Phase factors typically are plus or minus 1 in our case. So,
There's
it did
a
not
natural way of assigning the phase to be plus minus 1. There's some
Correct.
reality property or something like that.
Yeah, so that is what we are putting, but arbitrary phases we have not really tried.
No, but I'm saying that to know that something is phase plus or minus 1, that's a comparative statement. Plus or minus 1 compared to something.
See, thing is, this is what is dictated when you do when you write the monodromy matrices in conformal field theory. The monodromy matrices, when you have the monodromy matrices acting on this, what you get is not an arbitrary phase. This is only always plus or minus 1. This phase is not any arbitrary phase. So, this if it is R1, R2 and R, so this epsilon is and then you have a Q to the CR1 plus CR2 minus CR by 2.
Correct.
And this one is always plus or minus 1. This is what we call it as a Wigner 3J phase.
This is like the Bose-Fermi. This is the exchange like that. No, but what I was saying is suppose
And this is what is incorporated here.
Yeah, no, but that's in the nature of the block. Suppose you give me a block. I can take your block and multiply by any complex number. That's as good a block.
Okay.
With the same monotony.
Yeah, yeah,
Okay.
yeah,
Now, if you've got some way of normalizing it, that sets the norm of that number.
yeah.
But I want to know whether there was a natural way to set the phase of that.
But-
I understand CS is a very specific convention, but I couldn't understand what is the natural way. I didn't understand.
There must be
one
something
of
very
the one of the natural way, okay, so the specific convention is to match with the existing results of the mathematicians, right?
That is fine, but
See, you don't want to work completely differently, that if you have a fundamental representation, I have to get back the answers of Homefly, PT or Jones. And
I was just trying to learn.
so this dimension QT you can question, whether you want to put it with phase, without phase, all these things you can question. But if I play around with anything for all the tower of 10 crossing knots, I wouldn't have got the answers with the mathematicians. So in some sense, we are forced to make a choice, and we don't have a proof. This is by only fitting with the experimental data or whatever which is available. Not experimental, I mean computational data.
Let's call mathematics experiment.
Yeah.
We're doing theory.
No, I mean the data which is available in the literature, we have to first calibrate, right? And the calibration forced us to use this, not with any arbitrary phase.
Unitarity of the grading of monodromy matrices will not
See, then you have to do fusion rules, all these. Yeah, but if you are using an arbitrary phase which is dependent, and when you do fusion rules, then also it will get a combined.
Yeah, it will work. It's just a change of base connection.
Yeah, more generally you could add a unitary transformation.
Yeah, so then they will also have those properties, the conventional fusion rule properties, the phases also, right? Yeah. Okay. Okay, so this is what I was just trying to say, that what I showed there as these are nothing but the two different ways of combining three angular momentum in two different ways, and these two bases are equivalent bases and they are related by a matrix, and that matrix is what is called as a quantum Raka coefficient matrix. Okay, so using this basis and normalization and playing around for arbitrary, if you want to look at arbitrary knot, you have to try and look at arbitrary exchanges of punctures, which you put it as a arbitrary braid word. Okay. So if you take this is a 2 boundary with an arbitrary braid word, and you can have 3 boundaries, you can have R boundaries and so on. So we can write states for each one of them and then play around to, suppose I have an arbitrary braid of this type, it is not evolving from one boundary to another. If you see here, it goes from here and comes back here. There are non-trivial entanglements happening here. You can treat it like quasi-particles on the S2 boundaries evolving in time, and they have a non-trivial entanglement properties between this S2 boundary and this S2 boundary. Okay. So these are issues which you can see here showing up, and this particular state I do not know how to evaluate it, but I can redraw it as my conventional evolution states, but in the process I need to introduce another 3 manifold with 3 S2 boundaries, and if I glue all of them, I will get back this state. Okay. And similarly this one is same as this, but with odd number of crossings, and you can do, if you have it in the middle, the same thing. Sometimes we call this as a necklace. The necklace is in the middle, then what you see is you have to do one more time evolution braiding and glue it, and for each step I know how to write the state on this side, and I can write the state for this case. And this loop is also beautiful, that you can try and rewrite it in this fashion. So it's a very systematic exercise, that only price you pay is that you have to introduce 3 balls with more than 2 S2 boundaries. And this was also a good interesting thing, because now we could do topological entanglement between S2 boundaries by tracing out one of the S2 boundaries in this context, which couldn't have been done if we didn't know that this can be viewed like this, because quantifying is done using this piece, and qualitatively we do see some entanglement here. Okay.
So this cylinder can be thought of as an inner product between
out of, no, it's a tensor product of two boundary
So
states.
then-
Yeah. Okay, Hilbert space of S2 cross Hilbert space of
And then that is a tensor product of 3.
that is a tensor product of 3, and whenever you are gluing oppositely oriented, you take an inner product. So one of the boundaries gets removed. Okay. Okay, so these are the systematics, as I have said here, the braiding operator, and then your specific question, if it is anti-parallel, then we put in an anti-parallel braiding operator. If it is parallel, then we use the, if there are two parallel lines, then it is R cross R. If it is anti-parallel, then it is R cross R bar. These information we take care when we write the quadratic Casimir, whether we have to put an adjoint or a singlet here, or we have to put double box or double vertical box here, depends on that information. Okay?
No, the last previous slide,
Yeah.
the one before that. So like when you're sort of evaluating, let's say, an inner product or even an out product, like sometimes you would want to sort of insert a resolution of identity,
Huh.
essentially breaking up the sum into pieces.
Yeah.
So is the basis for this resolution of identity known?
So identity is like what? Anything without any crossing in between, right?
Yeah, that's the trivial braid.
Trivial braid. Yeah. So that you can write it with the, so that state is, what is the definition of an identity?
No, what I meant is that is there a basis?
It's there, that's the same basis, that's the 4-point conform block. Any basis you can choose, only thing is for this boundary, if you choose this, you can choose the same here, and then you write the state, this let me call it as a 2 boundary state. This I will write it with some coefficient, and the coefficient should be such that if I do nu2 and take another nu2 on it, okay. So this is boundary 1, boundary 2, and I will have a boundary 2 prime with which you have to take an inner product, and then have this with 3, and you should get back this with nu2 with this piece. When you do it with an appropriate inner product, you have to get the state which is as if it is nu2 with boundary 1 and boundary 3. That will decide for you what this coefficient is, and that coefficient will turn out to be 1. That is the only option I have. Okay.
Take the basis to be just a bunch of twists, right? Swaps. Yeah, yeah. 1 twist, 2 twists, 3 twists, and so on, up to
Yeah.
the number of the dimension of the Hilbert space.
Yeah.
I mean, there would be other twists that you could do, but there would be linear combinations of the.
Yeah.
spaces.
So the twist will be like braiding operator on this.
Yeah.
And then when you take the inner product, you have to remember what you have to do, and then it will make sure that you get back the, so if you do an inverse twist there and a twist here, they will cancel each other. One will be q to the power of something, the other one will be q to the power of q inverse to the power of something. They will cancel each other, and then you will get again the identity operation. So it's all consistent, topologically consistent, the construction. Yeah. Okay. So these are from the conformal field theory, these eigenvalues. Only thing is there is a subtle issue about this framing, but framing is just an overall factor such that whenever you draw a loop like this or draw a loop like this, I want the invariant to be same. That fixes some framing factor, but that's an overall factor. Okay. Also, sometimes mathematicians don't want these two invariants to be same. They say that we fix a blackboard frame. I am not allowed to go beyond the blackboard frame, which means that if I am not able to move out of the blackboard, then I cannot make it into this. So these two are called framed knots, which are different. They are invariants, and that the invariant difference is only in that framing number. So that's another way of mathematicians work. Okay. Okay, I have just shown you some kind of, I don't know, you can call it rangoli or whatever, but it's just that any knot which you give it to me, you can try and redraw them in a way using those building blocks. because I know how to compute here. If I want to do the computation for this state, I know the state to start with, then I know the braiding is in the middle strand, then I have to go to the side strand. I know one systematically to write the state for P5. Similarly, I can write the state for P4 where I will do that additional piece of set of moves which I showed you, and then this 3 boundary, this coefficient in fact is for the 2 boundary, but this coefficient was for a single boundary. If you remember, it was just root dimension qt. It turns out that it is r minus 2 by 2, something like this. So you have for 2 boundary you will have it to be coefficient to be 1, and for r boundaries you will have these coefficients to be for 1 boundary you will get it to be. So it's a very systematic way of fixing it, how to go to r boundary 3 balls. Okay. So only thing I want to point out here is that it appeared that any knot which is given in the Rolfson table, using my building blocks we could redraw them every time, where every boundary has only 4 punctured boundary. One of the reason why we worked with this is because 4 punctured conformal blocks were much more tractable. If I take this knot and draw it as if it is 6 punctures going to another boundary with 6 punctures, even that I can draw, but then it becomes difficult to compute, but we could redraw it using these building blocks where every S2 boundary has only 4 punctures. Okay. But this is not this exercise is not true for any arbitrary knot. Okay. So this is something which I was not aware of, and then at some point the Russians showed me the Conway paper in 1929. They call it as arborescent. In fact, you can see these things as a fat graphs or a tree diagram where you shrink all the 4 punctures and call it as a point, and then you can draw vertices like this for the 3 boundary situations and so on. So you can draw a nice tree which at the end means that it is capped, and in between if you have it's a 3 boundary, and you can also have 4 boundary, all kinds of things you can have, and you can draw it compactly like this and put in integers here. Especially you have to put in 3 integers in certain sequence depending upon crossing is in the middle strands or side strands and so on. One of the project which we took up was to draw it like a universal tree with so many parameters, and we wanted to write one invariant. If you change the parameters you will get all the up to 10 crossing Rolfson answer. But I think we missed about 30-40 knots, but almost all knots could fit into that tree. Okay, so the
why do you need it to be a tree? Why can't there be a loop in this skeleton?
no, this is what will happen. This diagram also I will split it up using the earlier one, no? This way. Everything will involve a tree with braid word.
No, but you're
Propagators
saying there are
also.
These knots,
Huh.
which are called arborescent knots,
Huh.
only those knots can be written this way.
Only those knots can be shorthand notation like a Feynman diagram. I can draw a shorthand notation like this.
Tree,
Ah.
skeleton tree. But for other knots, could you do the same thing but now allowing for loops? Because if you do, then physics
Allowing for-
computation-wise it would not be.
Allowing for loops, that is what I am saying. Then the computation we are not able to do it. You want to allow for loops, right?
But if you allow for loops, it's just still four puncture boundaries, right? Why
Anyway,
difficult
so
for
no,
one
it gets difficult. Anyway, some simple example like 817 we are not able to do that.
No, but what is the issue?
Huh? 818, right? Yeah, so 818 what happens is, so it involves a 6 punctured.
So that's what I was saying. Without going to 6 punctures, just 4 punctures, but allowing for loops in this skeleton.
Yeah, we have not been able to even do that. Anyway, so we can still think on it, but I don't think we were able to do that with just 4 punctures, right?
Yeah, 4 punctures.
No, it's not possible
You mean
at
this
least.
decomposition is not possible?
This
or what's the
decomposition is not allowing us to do it. even with a loop you are saying. What exactly you mean by loop? You just want a 4 here and then you want to put some.
No, so if you go to the next page, so next some more complicated tree business. Yeah, here for example, this tree that you have, this P3 and P5.
Huh.
P5,
Yeah.
which is at the bottom, and the P3 which is at the top right.
Yeah.
So they can go around. They
Correct.
can go around and connect like this.
No. That is not. Yeah, that's not allowed. Yeah.
No, but what you.
Anyway, you can.
What?
Because you need to get finally a knot,
Yeah.
and that what you're saying is go here, and then come back here. No, that's not allowed.
No, I'm saying that's not allowed, but I'm saying that is not an Arborescent knot, right?
That's
so far
not
you're
an
saying your technology is working for Arborescent.
Arborescent knot.
I was just wondering if this knot is not Arborescent in the way that this goes around like this.
Yes.
Are there any issues computing that?
That there is some issues about it. We can talk about it later. Yeah, I remember that also. It's not possible. Yeah. Okay. Yeah, okay. So I understand that. Just continue here and come back and join here. Those are not computable. Yeah. Okay. So and then there are links, and these are also interesting in the sense that we could now look at entanglement between different components of there are more than you see I put 2 different colors, it's 2 component link and 3 component link, and you can work out entanglement issues amongst different components within the Chern-Simons field theory framework. Okay. Okay, so this is, even though it looks like a messy result, but it is a very systematic thing that if I have drawn this diagram here, each one I know what is the state, and I just take an inner product and write the state. Okay. Only thing is that it will involve these Raka matrices, and as he pointed out, depending on the basis you can either have one type of this type, or you can have another type where the adjacent strands are anti-parallel. Okay. So these are 2 types which are going to show up, and these are the only 2 types which shows up in the context of Arborescent knots. Okay, so this is something which I thought I should stress here. Kirillov-Reshtkin, for this 3 representation associativity law, you can get the 6j symbol in a closed form expression. Okay. So we wanted to achieve this for SUN. Okay. So to achieve this, what we found with Satoshi and collaborators, Satoshi Zodin, what we found is that this is a good example, good class, which is called twist knots, where the invariant can be written using Chern-Simons way involving the one of these Wigner 6j, and there is an alternate way in which we could attempt this looking at the results of the mathematicians, and comparing these 2, we tried to extract this element for some simple representations, and then we went back and tried to write it in this form. Okay. So this is what we did, and key results are from the mathematicians' work. This is Biro and Mausam, who had written it for trefoil is the lowest in that twist class with positive integer, and figure 8 is in the lowest in the negative integer. So there is a pattern which is seen for the trefoil for positive integers, and these are like the Q binomial coefficients. So everything is like a Q number. Looking at this observation, we redid this for the SUN case. So this was done for the SU2. So we thought we will redo it for the SUN. In fact, we tried to redo it as if it is also the T variable included, like the categorification one, and it did work. Our guess and the existing data helped us to conjecture a form for it, and if you put T equal to -1, you will get the colored home fly PT. So this is what was the interesting thing which we could use, and then we also tried to minimize the summation with the aim of trying to check volume conjecture, and we could use the Bailey identities and bring it to a minimal summation. So once we had this result and comparing with the Chern-Simons answer, we could extract a closed form expression. Okay. So this is what is there in 2013. We had this paper, so you can take a look at it. Look almost similar to the Kirlo-Rishtikin, but there is slight modification.
For arbitrary representations or these many?
Only for symmetric, and this hard dot means it is conjugate of symmetric. So all the hard dots, if you had n1 to be 1, this will be like a vertical box of n minus 1 boxes. Okay. So only for this we have managed. That's a good point. We have not managed to do this beyond for arbitrary representation. One of the issues is that multiplicity issues, which is kind of a big barrier which does not allow us to write a closed form expression.
This classification is based on what? Type 1, type 2?
Yeah, type 1 means the adjacent two strands are anti-parallel. Type 2 is when adjacent two strands are parallel. Directions. So once the directions are parallel, I will use representation. If it is anti-parallel, I will put the conjugate of the representation. In SU2 it does not matter. So SU2, in fact, both the answers will match. When you put in the SUN n equal to 2, both the answers match, and for n not equal to 2, these two are distinct.
Can you check level and or something?
Huh?
Can you check level and kind of duality?
Here.
These representations will go to.
Yeah, the only thing is that I've kept the k to be free, n to be free. If you put a k to be specific, then the tensor product has to have the fusion rules are not arbitrary. You have to put a minimum of k minus, right?
Right, but probably can you compute their dual representations in the dual theory and check if there is nice mapping?
Because these, at least the q variables are e to the 2 pi I by k plus n, and the rank level, this is invariant.
It cares
I think
about the
inverted is saying
representation.
completely symmetric will go to completely antisymmetric.
That is available. The representation you are talking. Representations, yes. Yeah. No, that result is also available. Once I know this, I can, wherever it is a function of q for one of those coefficient, I can, function of q and a, I can say that if you replace this by this, then it becomes function of q inverse and a. That is available. This is what we call it as a mirror symmetry.
This is available by computation or available by the duality map? Is it a check?
It's a duality map and it is checked also. Yeah. No, I didn't understand that you wanted the conjugate. I was thinking about the, yeah, I agree. That is also a rank level in horizontal boxes go to a vertical box. Yeah.
When you check whether they are parallel or anti-parallel, you take the two-dimensional projection and then check.
Yeah.
But
Yeah.
then I can
See, you,
orient the lines in a different way that such that two parallels
Yeah.
become anti-parallel, because I can take the other one
No.
nearby.
if you take a simple knot, a curve, you draw the orientation on the curve first. Once you have fixed it, once you redraw it in terms of these building blocks, the relative orientation cannot be changed arbitrarily for a knot. Okay, so this is the expression which I said is very close. It's just that I use the weight vectors and take a dot product with the root vectors. Okay, so this is the only modification. There it was just J1, J2 and so on. So J1 will be lambda 1 dotted with alpha. That will give you the number. Yeah.
I should say that the 4 prong, a different top will be.
Yeah. So okay.
Sorry, this was a conjecture for the 6J symbol for these.
These two.
For
These two, yeah. So with the, you can see that there is a CZ coefficient, and that CZ coefficient is for type 1 and type 2 after looking at a couple of symmetric representation, kind of guess that it should be this, and we check some more symmetric representations. So that's the way. It's still a conjecture. There is no proof here, but it's still a conjecture. One of the things which we have been trying to do is at least to try and see whether it can be written as a Q hypergeometric series. That's not happening, but if that happens, at least we will get some insight for other representations. Okay, so what should I do? Should I stop here and get to volume conjecture some other time? Because if I start, okay, so anyway, let me just start off and maybe. So, thing is, so far we have looked at knot invariance, this is colored zones with arbitrary spin and so on. What is interesting is Keshev in 95, he tried to show that a topological quantity, the evaluation of a topological quantity can capture the volume of the corresponding, you take the knot, take the tubular neighborhood of the knot and remove it out of it, okay, in S3. That is what is called as a link complement or the knot complement. What he showed is that this expression which is on the left hand side is a topological quantity, that is a geometrical quantity, and these two are related, and he verified it for figure 8. Okay.
This is sort of classical.
Yeah. Yes, it continues. There are generalized volume conjectures and so on.
What do you mean classical?
The N is taken to be
No, N
large.
is color, not SU2 still.
No, N is large and Q tends to 1. So, in that sense he is saying it is classical, right?
Sorry, what is the, from a Chern-Simons point of view, this is Jones polynomial, right?
This is Jones polynomial, and put the variable to be nth root of unity and take the nth root of unity to be large.
But can you make it for SU?
SUN also you can.
I want it to level K. Can I think about it as
Oh, right,
K
right,
going to
yeah, sorry,
infinity or
yeah,
not?
I think it's that means that, yeah.
Huh?
Then it is like a classical level.
It is like a classical, that is what I said, the K is like the N,
Oh, so you are scaling
Large
both
K.
the spin and the K level together.
that is
Large
right,
spin.
yeah,
Sorry, yeah.
okay. So, it is a polynomial in variable Q, but you pre-place the Q also as the color and then take the color tending to infinity and find a functional.
So is there a way to understand this from Chern-Simons?
No, from Chern-Simons there is a different picture, I will show you that. Okay. So, from Chern-Simons we look at it as if it is SL2C Chern-Simons. We look at it as an SL2C Chern-Simons, and then you take the K, there will be, it is a complex Chern-Simons. So, you will write it as with the spin connection and Fierbein, you write the action and you can show that the leading term should be the volume of the 3 manifold.
And this limit makes connection to the SL2C. This limit of the SU2 makes connection to the SL2C.
This limit is conjectured to be SL2C by Gukov, but yeah, it has not been, yeah. Only thing here is, I just asked him why you did this, and he says that if you write the large color behavior, you can see that you can rewrite it in dilogarithms, and dilogarithms has information about volume, and then he proved it for one example and it worked for many examples. Okay, so I think I should stop here because I think yeah. So huh?
Just an announcement that Raju has managed some extra tea here for us. So this is a combined tea for the next one and so on, but we are supposed to keep for the
Actually, it was for the next seminar. Your seminar has been carried away.
This is for us.
we
No,
have
for
some,
next seminar.
we have less than half of it, right?
Yeah.
Okay. So then there is a generalization to, this is nothing but the zero locus of this will give you the space of flat connection in SL2C Chern-Simons. Okay. So here is where you do the double scaling limit. You take call this Q as a quantum deformation, put it as h cross tends to 0 is like Q tends to 1, and you take a double scaling limit where x is q to the power of n, which is e to the n h cross, n tends to infinity, h cross tends to 0, n h cross is fixed. So this limit can be expanded.
This volume conjecture thing, the right hand side, which is the volume stuff.
Volume.
That in principle depends on some cutoff, no, or not?
Yeah. So the maximum,
Just goes away.
it is the maximum volume of the 3 manifold which you can get by stacking ideal tetrahedra with dihedral angles as pi by 3.
I'm just saying that
What cutoff you are talking?
You cut out some tubular region.
That is a 3 manifold which will have the impression of this. Suppose I take, let me give you a simple example.
So that tube has some width.
Yeah, so we are not worried about those width.
So
It's
the
a,
result is independent of it.
that's right, that's right. So if you take an unknot here in S3, you thicken this piece and you remove it out. Okay, so you basically have a toral boundary here, which is like a 3 manifold, right? It's S3.
Yeah, you have. Yes. Do you need your tea?
So it's just you take the knot, thicken the knot, and remove it out, and whatever is left is a 3 manifold with a toral boundary. Just like the earlier one where I took a 3 ball with an S2 boundary, you can have a 3 ball with the toral boundary, 3 manifold with a toral. Take a cycle tube, it is a 3 manifold with a torus boundary. The air, including the air, it is the 3 manifold, right? Yeah.
I think the question is that like on the right hand side of the volume conjecture is a symmetrical state.
Yes.
Naively you think that the thickness of the tube would feature in.
Yeah, I am just saying you take the maximal volume of the 3 ball where you stack the ideal tetrahedra into it. Yeah.
Maybe we can
Yeah,
continue over
yeah.
chai at the end.
Yeah, yeah.